Okay, thank you very much and good afternoon again. Welcome to another lecture in the Australian Society of Exploration Geophysicists webinar series brought to you by the ACT. We're very lucky today to have Dr. Richard Blewett, who will be giving us a personal reflection on applied geophysics to the understanding of Australia's geology and mineral potential. Before I cross to Richard, I just want to go through a little bit of paperwork first. None of these lectures could come to you without the support of our corporate sponsors, Corporate Plus being High Size, Total Seismic and VelSeis, and Corporate being Southern Geoscience, Santos, Transparent Earth Geophysics and DUG. Along with our corporate sponsors, we have state branch sponsors. Unfortunately, there's no ACT branch sponsor yet, but we're more than keen to take up your offer. Please let me know. Okay, now the lecture will last for about 20 to 30 minutes. Please, any questions put in the Q&A session as opposed to the comment session, and the questions will be mostly answered after the talk finishes. Coming up on Tuesday, 6th of April, 6 p.m, we have the ASEG 2020 Annual General Meeting, and then that's followed the next day by a talk by Dr. Jack McCubbin on using airborne gravimetry data to improve the Australian model of zero heights. Remember all the wonderful benefits you get from being an ASEG member, reduced entry to the AGC, which comes up in September, free entry to regular technical events in your state, access to the annual wine offer, foster a professional network, research funding and travel scholarships, free membership for students and half price for retirees. Good. And also, please keep in touch with the ASEG through the monthly email newsletters, through Facebook, Twitter, LinkedIn, YouTube. You will find us everywhere. Okay, so before I pass to Richard, Dr. Richard Blewett is the principal of Geosystems Consulting, offering consulting services to industry, government and community on all aspects of mineral, energy and groundwater resources. Previously, Richard served 31 years for the National Geological Survey, Geoscience Australia, with roles ranging from the research scientist to senior executive, including leading the mineral system branch for 9 years. Richard is interested in the management and leadership of science and in geoscience education for the public. Okay, thank you. And I'll pass over to Richard.
Thank you, Mike. Can you hear me, Mike?
I can.
Okay, let's see if this works. Share screen. Is that working for you, Mike?
Yes, go ahead.
All right, look, thank you. I'll be closer to 30 minutes, not 20. So I want to thank you, Mike, for inviting me and the Society for also inviting me to reflect. This is a personal reflection, I guess, on geophysics applied to the understanding of Australia's geology and mineral potential.
Sorry, Richard, to interrupt, but you're in draft mode.
Really? Which screen? Okay. Okay. Stop sharing. That's not what I see here. Okay. How about this? Oops. Screen share. That's it. Got the wrong one. Sorry, Mike. How's that?
Perfect. Good.
All right. I won't repeat that. But look, I'm not a geophysicist. I'm a structural geologist by training, but have developed a great fondness for geophysics. I couldn't have done my job without geophysics and the geophysics community. So I'd like to acknowledge the discipline of geophysics, particularly for making me a more honest geologist in terms of the tests that are available to us as geologists through the use of geophysics. To the many wonderful geophysicists I've had the pleasure to work with and the honour to lead here at Geoscience Australia for the last 8 or 9 years, I also would like to acknowledge the Met sector, the people who are out there collecting a lot of the wonderful data, the images I'll be showing you. We couldn't do what we do without their wonderful work. And I'd also like to acknowledge my late friends, Barry Drummond, Peter Milligan, and Richard Lane. We miss you dearly. We've got a really hard problem trying to look into the solid Earth, much harder than the astronomers who have this transparent atmosphere, a vacuum of space, and a bright dot on a black background. Whereas us geoscientists, we've got a landscape like you can see through here, the Barclay tableland. We really have little idea of what's beneath our feet without the use of technologies such as geophysics. So it's really important what we do as well in terms of our well-being as a country and as people, in terms of the resources that come out of the ground. So geophysics is a key part of us as people. I also think our profile's rather low compared to the astronomers, who seem to get not only lots of money, but also lots of airtime. And the sort of science that we do as geoscientists, and particularly you as the geophysics community, making those wonderful images of the Earth, of the deep Earth. And I think there's an opportunity there in terms of educating people about the wonder of science and the wonder of Earth science. I've had the great pleasure of working in a wonderful organisation, Geoscience Australia. I started when it was BMR, through the change to ASEG, and to now Geoscience Australia. It's a remarkable organisation that was founded 75 years ago. So it's the birthday of this agency. And it's been led by wonderful people and visionary people setting up the organisation to systematically map the continent, to understand the resources potential. That's what the original BMR was set up to do. And my job over the last 30 odd years has been to continue to do that. So it's been a great privilege and pleasure to be able to continue with that work and to be able to add to the crown jewels. When I walk into this building, I look up at the great big maps of gravity and radiometrics and magnetics and the geology and think, my goodness, this is just remarkable that we're so well placed here in Australia in terms of these sorts of data sets. What could I do to help add to these? And I'll be reflecting on some of that throughout the talk. I had also the fortune to be able to sort of shape a strategy, and that was the National Mineral Exploration Strategy. And what that is, it's an agreement between, or a strategy between Geoscience Australia and the State and Northern Territory Geological Surveys. And it basically brings us together and provides a major competitive advantage over other jurisdictions that have mineral resources. And you can see the fruits of that collaboration in this map that's over on this side, which are some of the more recent larger geophysical activities that are happening right across the continent and in every state and territory. Absolutely remarkable. So continuing that sort of vision that Sir Harold Braggett had when he set the BMR up to continue to map this continent in great richness. The other aspect of the strategy was to be able to take not just the data, but also the pre-competitive tools and convert them into something that people can make decisions from. So I'm really, really pleased with how the portal's been going. So for me, that's been an aha moment to see how well that's going forward. Back in 2010, Phil McFadden from the Academy of Science convened the Uncover series of workshops, and this has continued on for the last decade. So this was really recognising that there was a problem of discovery or lack of discovery, and that we needed to bring science to bear on solving this problem of diminishing discovery despite quite a lot of expenditure at the time. And so the Uncover Roadmap was born. And geophysics plays a major role in unlocking the potential of Australia through these activities. And geophysics is in the highest and high priority areas: about cover, about footprints, about starting to do some of these big national surveys like AusAEM, AusLAMP, and gravity, continuing to do with gravity, the AusArray survey in through here, and so on and so forth. So when I had the opportunity with writing to bid to government to get funding for the original Exploring for the Future, I was able to draw on this work there, or these sets of activities, and put serious money into progressing some of these big geophysical programs that we're seeing wonderful results from now. So it was a great privilege to have that opportunity, and I think it's going to put Australia in a great position. So we're faced with a landscape such as this. This is the wonderful Barclay tableland with the seismic trucks trundling across it. And, what we want to do is peel off that surface and look beneath, through the basins and the cover that might be hiding the mineral deposits, into the crust, the crystalline crust, the basement, and even into the lithospheric mantle. because mineral deposits are part of a mineral system, and a mineral system has huge length scales across the whole lithospheric column. And so being able to design the science programs that I've been involved with was very much shaped by the Amira and Uncover roadmaps. So adding to those crown jewels that I showed early on in the talk, I just want to go systematically down through the lithospheric column, starting at the surface. We've got these wonderful data sets now that really map and image the surface in ways that we were never able to do some 30 years ago when I first started. I was recruited in 1990 and went up to Cape York to map with the GSQ guys. We had a joint project there. And the first bits of material, well, reference frame that I had to work with were stereo aerial photographs. Now, some of the time I didn't even know where I was using these things. It was pre-GPS, at least GPS that we didn't have. So yes, you can make a bit of a start to understand the surface based on aerial photography. But as I said, there's been this wonderful array of new data sets that are coming on stream now and over the last decades or so, and LiDAR is one of those. I'm not so sure that great use has been made of these in the mineral exploration area, but certainly in the groundwater. I had the pleasure of working with the groundwater team for a couple of years back now, and could see the benefits of LiDAR. But I do see the benefits of LiDAR for MinEx in terms of understanding the landscape, geochemical sampling, regolith mapping, and so on. And they're just wonderful pieces of art too. You could make a tie out of those, I think, or pretty garish. Changing sort of scales in terms of the shape of the surface. This is some pretty neat work that John Wilford had done. And of course, it requires things like supercomputers to be able to do this. So here's looking at the national DEM and trying to look at it from three scales, a broad regional scale, a more local scale, and a finer local scale. And the subtleties that you can see in this landscape, rather than just imaging it up typically as we see, is really borne fruit here. And I wonder with these sort of multi-scales, I haven't seen it done, but I'm sure you could apply the same codes to potential field data to see the different wavelengths of data. I'm sure it'll give you different views of the Earth. And there's lots of data that's being collected these days, not so much by the minerals team at Geoscience Australia, but across the agency and across the states and territories. So there's lots of elevation data that's out there now for that. Back to Cape York. So it was the beginning of the National Geoscience Mapping Accord, where we were really for the first time bringing geophysics mapping and geological mapping together at least on the same sheet. It seems obvious. I mean, it's obvious now, but it hadn't really been done systematically before. And so it was a great pleasure to deal with people like Brian Minty and Peter Wellman to be able to map chemistry effectively from the air. You can see these wonderful fans of materials, and it's giving you something about the chemistry of these. You can see the difference of the Yambo inlier and the Cohen inlier, and the in situ regolith. It was really difficult to map off those aerial photographs, but having access to radiometrics was just a fantastic source of information about chemistry of the near surface. After Cape York, I went over to the Pilbara, worked with the GSWA. We were mapping over there. Now the Pilbara is quite a different beast. Not only is it Archean, but it's incredibly well exposed in places. So this is the North Shore sheet on the Marble Park 250,000 sheet. Absolutely fantastic geology, almost 100% exposure. And it was interesting talking to people who were mapping over there, the need for geophysics. Because the idea was that you could just see it all, but still a big area to cover. And the radiometrics, sorry, what I'm showing there is Landsat mapping of the surface of the Pilbara. Absolutely fantastic, giving us an indication of the clays, the iron oxides, and the silica. I also had the pleasure of working with Phil Beerwith from the ANU at hyperspectral mapping, and again, mineral mapping, pyrophyllite and white mica. And this is associated with slightly more covered areas, and you can see the mineral system footprints in these data. And this has been taken to a really new scale with the Digital Earth Australia team here at GA, and Dale Roberts in particular from the ANU, in taking Landsat data across in terms of a data cube. It's cloud-free and making the greenest Earth picture of Australia. The inverse of that is, or the opposite of that is the barest Earth, which is getting us closer to the soils and rocks, the surface materials. not influenced so much by vegetation. So we start, again, getting those wonderful clay, iron and silica first-order chemical maps that we can have of the surface. So we've got these wonderful data sets that have moved so far from black and white aerial photography. We've also got other data sets that give us a sense of what's the thickness of the cover or the nature of the basins, the nature and thickness of the cover in the basins. So I'll talk about some of that. So these are new jewels in the crown that are being developed. Because the challenge we faced, and this really came to us when we started drilling. The first drilling was down in the Staveley, down there in Western Victoria. We didn't want to spend too much money drilling deep, deep holes when we could intersect basement, which we were interested in other areas where it was perhaps shallower. And when you look at a sort of a national map like the sea base map, and it's no criticism of the sea base map, but others having an attempt at trying to map the thickness of cover or the depth to basement, we get wildly different estimates, and they range from +2 kilometres to -2 kilometres. So really, we weren't going to spend a lot of money doing that. We wanted to get better at being able to define the thickness of cover. And so, as part of the Uncover workshop, we convened this theme. We convened a workshop in Adelaide back in 2014, and it's only half the crew that were actually at the workshop. There was some 35 people or so. We really wanted to understand from the geophysical community the wisdom of the crowd. And in summary, what we found was that you really need to know the geology and the rock properties of the basement and the cover, and how they change across the continent. You need to be able to benchmark your methods against a known reference, exactly like drill holes. Another key finding was don't give up on a method, but try different processes. And I'll show an example of that. Know and store your uncertainty, and there's no silver bullet for this work. So in terms of benchmarking, after the Staveley, we started drilling up in the Thompson with GSQ and the New South Wales Survey. And this is work from James Goodwin and others. And you can see here are these known drill holes where we actually finally did drill. But prior to drilling, we actually went out and collected a whole bunch of data. And what we're doing is testing the different methods. And you can see in some, they all work very well. In ULO 1, the seismic refraction doesn't have enough energy to get to the deeper parts of the Cunnamulla. But if you go up at ULO 2, you find that the targeted magnetic inversion doesn't give you a good result. And the refraction in the MT is the best. So it's really, even though this is one province, different methods are going to work in different areas. You really need to understand the basement and the cover. And similarly, after that, we moved over to South Australia to work with the South Australian surveys under the Nullarbor, the Eucla Basin, and deployed a range of methods, passive seismic and AMT-MT. And it's a tricky place. Not only is it quite deep under the Eucla, but really quite variable geology from sort of limestones to sort of squidgy shales and so on. So a lot of the methods weren't working, and even the MT wasn't working until Lawrence took Ross Brody's Monte Carlo codes and applied these probabilistic codes to the MT and got a fantastic result. So again, don't give up on a method. It's the method might be there, it's just the way you process it. And we've got lots of opportunities to process data in many different ways to get the result we want. So what we've been able to do is build up a portfolio of methods for different regions based on the different natures of cover and basement and their depths. Really pleased when we got the Exploring for the Future money to invest heavily and kick off the ASEG program. And it's really, I know it's even more extensive than this now. And Queensland funded this survey over there in around Mount Isa, and WA flying the Yilgarn. Absolutely fantastic. And being able to nest in this 20-kilometre line-spaced AEM, the higher resolution groundwater studies, it's absolutely beautiful work for mapping the thickness and nature of cover, even seeing conductors in basement, and of course, groundwater. We got quite a bit of criticism in some quarters for choosing the 20-kilometre flight lines, but I think these sort of maps are just showing how valuable it is. And of course, the opportunity to do infill flying by industries, sort of augmenting and helping this along. But it's all very well having these data. We need to benchmark not only the data, but how we actually collect it. It's AEM, but there are different platforms. And so I really commend Yusin for his benchmark test range over there near Menindee. So it's a well-characterised piece of geology with drill holes, well understood, and getting the contractors to fly over the same piece of geology across those control points really helps us understand the different methods. And similarly, in terms of how we process the codes, there is a number of codes out there, and I really again commend Ross Brody for his codes and publishing them openly in terms of putting them on the GitHub. And it's great to see others using these codes. So these are part of that pre-competitive code base and tool set that I talked about earlier. So we've got all these estimates of depth. What do you do with them? So again, this is a brainchild of Coral Chanota, and it came out of the Uncover workshop. He formulated this database called ASEG, and what it stores is these estimates of the geological and geophysical surfaces. It pins a horizon, whether it's the base of the Mesozoic or the base of the Cretaceous or whatever you choose to have, with the metadata about the method. And so we can start building really decent 3D maps of time and space and depth with confidence. So here we see Cenozoic all the way down into the Paleoproterozoic in terms of depths and their confidence levels. An important piece of work, and I take it you'll be doing this across the country. I'm looking at Murray Ord in the audience there. So we've looked at the surface, we've looked at the cover and the basins. The real sort of workhorses of a lot of the geophysical work that's done here at Geoscience Australia and pretty much everywhere in terms of trying to understand deeper geology is the gravity and magnetics. And of course, one of my faves is the seismic reflection. You know, I couldn't think of any real discovery that wouldn't have been made without reference to those two data sets in particular, the magnetics and gravity. So back up to Cape York. So this is how we used to map, or the BMR used to map. Pretty much the surface. Really, geophysics wasn't particularly well integrated in there, although we used to put the gravity field on there in terms of contours. But sort of moving forward and being able to work together with the geophysicists and have the data sets at the same time to help us interpret what we saw with the radiometrics, but also starting to make solid geologies and make sensible predictions about what lies beneath that cover. We didn't have a particularly good understanding or didn't really think about the thickness of that cover. That comes later in terms of my journey, my aha moment. And how that's been scaled up, sort of work by Alistair Stewart, again, off these workhorse data sets, the magnetics and gravity, and the compiled boreholes that constrain it. And here's a map of Northern Australia, of base of the Neoproterozoic, an absolutely remarkable map. And being able to punch that into 3D is just fantastic, who would have thought. So I mentioned that I moved from Cape York to the Pilbara. One of the challenges there was Archean tectonics. It's a bit of a different beast, and trying to explain what these dome and basins were. Now, it's not just an academic argument, but it often is. It's important to understand how the Earth works, obviously. But the idea is that you had these thick, dense greenstone belts sitting on a less dense granitic gneissic substrate, and this is density instability leads to something called sagduction. So one of the tests, of course, of this is gravity. And what you find is that there's just not enough mass to account for these sorts of cartoons. Often they're not drawn to scale by the proponents of the diaperic model. So I had some fun and games with the diaperists with the geophysics. Just going over to this sheet, we saw the Landsat of that area. That's the North Pole area, and we'll just head over into there. So you can see this granite in through here. It's a little window. It was actually thought at the time to be the tip of a big batholith. But then when you look at the gravity, there's a certain amount of mass there. So it really can't be the tip of a batholith. This is only a little thin sill. And in fact, this is where I moved into working with the geophysicists in terms of forward modelling. And this started to give me the sense of what's happening into the third dimension. And you can see that little granite body there, and the greenstones are only 5 k's thick. So if that sagduction process had worked, we've got a lot of missing mafic rocks, and maybe they were there once and have fallen away. But there are consequences for that. into 2000, I shifted south into the Eastern Goldfields, and I spent about 10 years in the Eastern Goldfields. It's a fantastic place, and I'd love to get back there. And I worked with Mike Barlow, and inverse modelling. So again, it's using the gravity data in this case, and this was a great first image for me in terms of understanding the shape of these greenstone belts at depth. And these domes that I talked about in the Pilbara, somewhat different in the Yilgarn, but again, we're starting to see the shapes of these. And it turns out these domes are really important in terms of focusing the gold mineralization. At the time, with Richard and Adrian Hitchman, started playing a little bit with GeoModeler, but we really didn't take it that far. But I do think there is great merit in where the 3D Loop Consortium is going in terms of implicit modelling, because building serial sections and the more explicit modelling that I've been doing is very labour intensive, and of course highly user bias is probably too strong a word, but highly influenced by that. So letting the data sing a bit better. I think there's great opportunities going forward with that. But in terms of those inversions, using, in fact, it was just this codes, the UBC codes. This is some work from James Goodwin up in the Northern Territory and across to Mount Isa. The scales of these areas we can invert using the computer power that we have now is fantastic. And James is telling me that he'll look to invert the whole country, but tile by tile at the moment. And we can start then not only just looking at shapes, we can start getting into mineralogy, like exploring then the magnetic susceptibility and putting isosurfaces around this, or looking at the density and putting, again, isosurfaces around that about particular minerals that we might, and rocks that we think that might be there. And pull these together and start pairing up magnetic susceptibility highs with density highs, which is one of the indicators of certain types of iron oxide copper gold deposits. And of course, this East Tenet area is an emerging ASEG province. So I think it's really cool that we can start to get into mineralogy through the potential fields like this. As I said, one of my faves is deep crustal seismic. Before I started my PhD and after my honours, I spent a year in South Africa on a seismic crew, acquiring low velocity layers and calculating statics. And it's great to see how far Australia has progressed in terms of the massive transects that were envisaged by the ANSA group. And we've pretty much done many of those and will continue to do that. But Australia's really got the best seismic network in the world. And it's really paid dividends in understanding the architecture and the geodynamics of the continent. I'll just talk a couple of seismic lines. This one's EGF1 near Kalgoorlie, and then the NY1 near Leonora and Laverton. Ones that I had something to do with. I didn't have so much to do with this. This was Bruce Golby and Barry Drummond. They had the balls to, I'm sorry, I can't say that. They had the heart, the great heart to shoot hard rock seismic, dynamite. And it, when we look at what we can do today, it does look a bit sketchy. They were brave, and again, they took a lot of criticism, but they were able to see some of these big fundamental structures that control the gold. And then, just step forward just a decade, and this is in 2001, working with Leonie Jones, and she reprocessed that full continental seismic, full crustal seismic line, and starting to get into the upper crust. And we were then able to relate what we could see in the pit of Sons of Gwalia with the kinematics of the shear zones, these SC fabrics, in terms of what we're seeing actually in the reflectivity. And of course, that extends right down through the whole crust. So I was just looking at a little area up in here near Leonora, and we see these big shear zones that break the crust up are in fact extensional shear zones. Yes, they've got some contraction on them, but fundamentally formed by extension, and we hadn't really appreciated that. It turns out that these big shear zones next to them, adjacent to them, are the goldfields, like Leonora, Laverton. And we speculated, Bruce and I, would go out and give talks about the potential out here in the Yamana Belt. And of course, about a decade after that, Gold Road Resources discovered Gruyere, a 6 million ounce deposit. So it's really opened up that whole far eastern frontier of the Yilgarn, Eastern Goldfields. And we see other features in the seismic, these domed, these domes, which we saw in the potential fields, but we're seeing them also in the seismic. Again, gave us a much better understanding of the architecture. And the seismic, in terms of the network that we had, we were able to build some really quite sophisticated 3D maps, absolutely tremendous. and use those to predict where minerals might be elsewhere. And of course, going forward into the 2020s now, the processing and the acquisition is so sophisticated. The team can even shoot across the highlands of Australia, some of the hardest country you'd think, you would have thought it was impossible, but they did it, and it's absolutely remarkable. This looks like an ammonite suture. It's so convoluted, but they're able to recover amazing data sets and get a great understanding of the Alps. So this was work with just New South Wales and GS Victoria. And what do we do with all that? So we've got all these big features. Well, we can start putting them together into these wonderful maps. So this is work by Russell Korsch and Michael Dublier to really understand how Australia was put together in terms of the fundamental boundaries of the jigsaw. And of course, these then get input into mineral systems models. I talked about the scale of the system earlier on. So part of the team were able to use these data and start inputting them into a mineral systems model. And we went over to Perth and gave a day-long workshop on the mineral potential of nickel, copper, platinum group elements, and showed this map here. And over in this area, just east of Perth, as the participants at the meeting went in and pegged the ground, and it's now a whole new province, nickel province, and Julimar was discovered. So these data have profound impacts on understanding the evolution of the continent and making mineral prediction maps. Just flipping down deeper into the mantle. Great methods, again, AusLAMP and AusArray, they're so pleased that we've been able to invest heavily in those. They're again recognised as very high priorities in the Uncover roadmap. I'm going to dip a little bit into the crust as well, so I won't just be sticking into the mantle, but I'll be talking about MT and passive seismic now. So here we go. The map, they're not current. The current that I've got. I'm sure the arrays have progressed since these slides were made. But nevertheless, great progress in terms of coverage of passive seismic and magnetotellurics, long period MT. And I'll show two areas, and I'll flick between the Yilgarn again and up in the East Tennant area. So back to the Yilgarn. So back in the early 2000s, I was working with Indrajit Roy and Graham Heinsohn, and we went along that seismic line, EGF1, just north of Kalgoorlie. I was interested in terms of what we could see in terms of conductivity structure against that architecture. And it turns out the Kalgoorlie belt, the Kalgoorlie deposit and the deposits that sit along strike from it sit in this golden corridor, and it's in fact an area of enhanced conductivity. And it sits above a ballooned out high conductivity region up in the mantle. You can see the big faults that we've built. So that gave me a real confidence that MT can do and provide something useful to us. So again, when the opportunity came to invest in MT, I was straight onto it. I'll come back to this little pinky thing here. This is an isosurface from the Skippy data, so passive seismic data. So in terms of MT, up into the East Tennant, you can see a 30-kilometre slice, and you can see this conductivity zone coming through here in East Tennant, striking east-northeast. And the team then jumped in and put some broadband instruments down and was able to get much finer resolution. Because one of the challenges is when you're down there in the mantle and the lower crust, people go, well, that's just so far away, how relevant is it? Well, great work by Weng Ping was able to show how these high conductivity zones have fingers that go right up to the surface. And here we go, zooming in, and even with the AEM flown over a drill hole that was previously there that we knew there was alteration in, and you can see that conductivity. So I think EM is fantastic for connecting the dots from the deep earth right up to the surface. And I'm sure we're going to see lots more of this sort of work. Back to the Yilgarn and back in time. So this is into the 2000s again, using the OSREM and the Skippy models. So I'm looking to the north, sort of obliquely down onto the Yilgarn craton, and there's that funny pinky isosurface. It's a 4.8 kilometre per second shear wave velocity isosurface. Greg Hall, who worked for Placer, was convinced that the gold systems were linked to features deep down in the mantle, and so we put this together. And it's interesting, just project those boundaries to the surface and look at the sort of melts that come out of that sort of depths in the mantle, these metasomatized melts, things like lamprifiers and carbonatites, kimberlites, no, not kimberlites, and cyanites, sorry, and also where the gold deposits are. And we see Kalgoorlie sits again on one of these edges. So, yeah, this is very first order. We speculated that maybe there are other areas, and it turns out that Gruyere, the deposit I noted on the seismic section, is sitting out on one of these edges. So impassive seismic, but coming up into the crust and much higher fidelity and finer resolutions, work by Babak and Alexi up there in the NT Queensland. Seeing starting to see a basin that we didn't know existed. In fact, a deep seismic reflection line was shot over it, but from first orders, you'd see it, that there was this low velocity zone in here, and it represents the Carrara subbasin. Fantastic coming out of there. But also, as we go a little bit deeper, down towards 10 and 12 kilometres, again, this east-northeast striking patterns of faster and more intermediate velocity layers are telling us something about not only the architecture, but something towards the rock properties of this material down there. So combining that with the MT, it's really giving a great understanding of what that deeper part of the crust is. And some, again, remarkable work by Karol Chanoda and his colleagues at Harvard and Cambridge and ANU is the base of the plate. So this is looking at the seismology of the lithosphere boundary. And we see an inflection in through here, and yes, it's coloured up, and you could argue, well, we're just on that colour, but here's the actual gradient there. These are Mount Isa over towards MacArthur River and the deposits associated with that Carpentaria belt. And there's a global pattern, in fact, that these sorts of deposits, these basin-hosted base metal deposits, sit on this 170 kilometre inflection in the lithosphere boundary. Quite remarkable. So the deep earth is really talking to the nearer upper crust where these deposits are forming in these basins. So this is a remarkable piece of work. So I'm just going to wrap up now and just reflect on a few things that I think are important going forward. This was some work that Richard Chopping and James Cleverly did, and I haven't really seen much of it since. So really what it's doing is looking at geochemistry and then modelling the geophysics response from it. It was pretty cool. So this is a synthetic model, but they took the work further on and looked at the St Ives Goldfield, and was able to show that you can model the chemistry and the alteration, turn that into rock properties, and see a difference in what you would expect from your understanding of the architecture. So it's again playing with forward modelling, but both with chemistry and geophysics. And I'd like to see more of this sort of work done. And it's sort of happening here with LithMod. This is work from Juan Carlos Alfonso, and Marcus Haynes was able to apply some of this work to Australia here, because we know we have one Earth and we've got all these different sort of lenses that we apply to it. It's very difficult to explain what's happening down there in terms of the actual rocks and the minerals that make up those rocks. And so LithMod is one way of actually getting into the problem using a Bayesian probabilistic framework. So we're starting to get other estimates of the lithosphere boundary, the percentage volume of melts, the temperature of the lithosphere, into the magnesium numbers, and so on. So really sophisticated work. And another bit is we've got all these wonderful data sets that we can sort of line up together. And here's an example of taking the airborne ear wide space line spacing and actually making a predictive soil salinity map from it. So it's again work with John Wilford and Newsom. And I think we've got lots of opportunities to play more with machine learning and AI with all these wonderful data sets. Really, your imagination will be your limit. So this is my last slide. So in terms of my journey and my personal reflection, I hope it hasn't been self-indulgent, but very much here I am mapping in my honours. All I could really deal with is what I could see at the outcrop and at the surface. I've progressed through my career to working with a fantastic group of people who are able to provide the imagery that allows me to see deep into the earth, even into the bottom of the plate, and take that understanding and lead to new mineral discovery across Australia. So I'll leave it there. Thank you.
Thank you very much, Richard. That was a fantastic, brilliant journey through pre-competitive data there that this country is blessed with. I'd just ask, I'll open it up to questions, and if there are questions from the audience, the physical audience, if you could just repeat them to the VC people, Richard. Thanks. Okay, so any questions, please?
Any questions? About 15 people in the room. No questions. So if you could.
No, actually, I'll start it off, Richard. Look, pre-competitive data sets, you know very well that some of those data sets are only partially acquired across Australia, or they're poor resolution. If you could pick one geophysical data set to acquire at higher resolution or to fill the gaps in Australia for the next round of undercover mineral discoveries, which one would you pick?
That? You didn't like it. It's a lot of work for you, Mike.
No, I didn't hear the answer.
Oh. I said gravity gradiometry.
Okay. Would you like to explain a little bit more as to why?
One thing, gravity, it's one of those fundamental rock properties that's telling us that we can get closer, I think, in terms of what those materials might be. Being able to fly them as well, it gives us an opportunity to get across the country without having to get onto the land. It's getting closer spaced and higher resolution gravity, again with the gradients and the full tensors, will get us ways into the geology that we haven't had before, certainly at the scale that we're talking about, and it would get sort of closer to the magnetics in terms of its sort of, I guess, fineness of resolution. And gives us a bit more depth than we can see in the magnetics as well. We've got that depth information within it. So I love gravity. It's often the first data set I look at when I look at an area.
Okay.
I find magnetics you can get a little bit confused with not so much the noise, but the less important things, but the fundamental structures come through in gravity. So that would just be a pick. I think I want them all, of course, but that would be one I would recommend. The passive seismic would be another one.
Okay. A question from Marina. What was your career highlight?
Who's it from, Marina?
Yes.
Working with you, Marina. My career highlight. Oh, gosh. Actually, it's a number of highlights. Look, I had the great privilege of leading a fantastic team who just did the most amazing work. And being able to stand up here about 8 months ago when the Exploring for the Future was finally delivered, and seeing a young team who I've been mentoring and working with, and you, Mike, and the other directors have been mentoring and working with, deliver a most amazing summary of what was found by the Exploring for the Future program, was just very gratifying, because I knew Australia was in good hands, because there's so much talent there, and they just did a fantastic job of not only doing the work but also communicating it. So that was a highlight. Really. It was So I mean, the thing is, my career has been in 3 parts really. So the first is as sort of a research scientist, then as a a leader of projects, and then but still doing research science. I wrote a book in the middle, and then leading a team of just amazing people. So it's sort of hard to pick. There's highlights all the way through, but I think really the culmination of my career was just watching the team deliver here back in July last year, the amazing Exploring for the Future highlights work. Yeah.
Okay, look, we have a question here from Mark Arundel, and it's a very good question, because I guess at the end of it, irrespective of how much geophysics, geology and geochemistry apply, at the end of the day, it comes down to the lie detector, which is drilling. So should GA consider setting up a drilling operation itself again?
No, I don't think so. I think through MinXCRC, I think there's ways forward. Look, I don't work for GA anymore, so I mean, I can say what I like, but I don't think that's right. I mean, I saw how VMR got rid of the ship, got rid of the plane, got rid of the drill rigs and things like that. But collect now, not so much offshore, because there's not so much funds for offshore shipborne work, but in terms of the amount of magnetics, gravity, radiometrics, and all that sort of stuff, even drilling that we collect now is way more than we ever collected, having the equipment in-house, or even the seismic trucks. You know, having really good contractors out there who are able to keep the technology current, the latest software, and not have to deal with the overheads and the depreciation of the equipment. No, I wouldn't think you'd need to have your own drilling rigs. There are others who are better drillers. You just point them where to go. And I mean, there's a team here doing it, and there's a whole consortium doing it, MinXCRC, another $200 million program. And it's doing great results. But it's a good question.
Okay, a question from Joe Kakuza. Ever since the advent of image processing of aeromagnetics in the 80s, the application towards understanding structural geology has been truly game-changing. But few geologists really understand the physics of magnetics. To what extent do you see this as a problem? That is, geologists' understanding of geophysics.
I think it is a problem. And I suffer from that too. And that's why I surround myself with people like you, Mike, and other good geophysicists. Yeah, I think being a lone wolf geologist could be a bit dangerous. Understanding things like remnants and things like that, how data are put together, how things are processed. I agree. There are lots of tricks and traps, and it's a specialist field in itself. So one thing I've learned from my career is the more diversity you have in your team in terms of your skill sets, the much better you're going to be. So I agree with you, Joe.
Okay, there's a lot of acknowledgements here for a fantastic talk, Richard, Ted Tyne, and Grant Butler. Any questions from the audience there?
Yeah, Anand has one.
So the question I have is, we see this trend towards integration of various data sets, and that's great. But also, you want some data sets to provide independent verification of the conclusion that you've drawn. So where is that balance between looking at data sets to provide independent verification versus munging everything together to provide an inference?
Okay, so the question was, did you hear that, Mike, or shall I repeat it?
Yeah, please repeat it, thanks.
Okay, it was a very long question, but basically, how do you verify data rather than just try and munch it all together, like in a machine learning thing, I suppose, is what you're getting at. That, I guess, from a geologist perspective, is going back to the obviously the rock, the mineral, the rocks and minerals, which we can drill to a couple of kilometres. Once we get beyond that, we're then having to infer what those materials might be. However, there are parts of the world where you see different crustal levels exposed. So experiments could be done on applying that method to those pieces of crust that are at the surface versus at depth. But I mean, we see that as provinces go undercover. So often we start in an area that's outcropping, we get to really understand it, and we chase it undercover and extend our knowledge from that. The other one is melts. So you can infer, again, so it's an inference. There's a lot of geochemistry and geochemical modeling that could be done to get at the problem. You can do a lot of measurements of xenoliths, so getting into the deep earth as well, the mantle xenoliths. And so there's been some good work done on that, particularly from the diamond type people. They really understand those geotherms, and they're able to measure them. They can put them in rigs and actually recreate those pressures and temperatures, grow those minerals, and see how they perform to other external fields applied to them, for instance. So that's another way of getting at it. But it's not dissimilar to our astronomer friends, sitting here on Earth or having a Hubble telescope. These other things are distant from us. So we're having to make inferences, no doubt. I hope that answers your question. But you can't beat a rock. You can't beat a stick of rock, because at the end of the day, that's what we're trying to image, and there's only one Earth.
Okay, a question here from the ASEG. Would you care to offer pointers to young geoscientists?
Keep your passion. Keep your passion. What I would say, stay passionate. Is that a good enough answer?
Yes. Okay. Well, look. Yes, and I've got a yep there from the ASEG. So look, any further questions? Otherwise, we'll leave it there and thank Richard for a fantastic talk.
I'm going to answer that question a bit better.
Okay, sure.
Yeah, look, don't assume because some old great guy says something that it's true. Back to first principles and really critical thinking. Just because someone's drawn a line in the sand or said something or written that paper doesn't mean it's right. So my advice to young people is maintain that curiosity as well as your passion, but also be skeptical and question. Obviously in polite ways, but yeah, I think that's what I've learned over the time. There's lots of myths out there, and particularly in geology, maybe not so many myths in geophysics because you're a bit more rigorous than us. But there are lots of myths out there. So be a good scientist. Follow the scientific principles.
Okay, well, I will close it there. Thank you again, Richard. And yep, I just mentioned to the audience again, keep in mind Dr. Jack McCubbin's talk coming up just after Easter. Thank you again. Thank you.